Good evening and welcome to our latest video on metaphysics and alternative health and how it all works together, how we work. It's a little bit of everything, folks. We are going to go over some very basic stuff. This will probably be a short video, but very important. This next few videos are going to be going through some nomenclature, some some definitions. Let me see if I can get this a little bit better here. Yeah, like that. One of the things I think that many people get confused on inside the human body and medicine enzyme. Exactly what is it? What does it do in the human body? And there are many cases outside the human body and through the universe where enzymes do their work, but nowhere is it more used than in the human body itself. And the other one is hormones. And I think we've all heard of both these terms, but I think some people might actually get the two confused, think they're the same thing, or and they really, at some points, they do work together. But let's start with hormones. Let's do this. The best way to describe the difference. Let's start with hormones. It doesn't matter which one to start with. You have two types of main glands that produce them. Your endocrine glands and they call exocrine. The difference is one is just injects in its hormone that it produces, it injects into a duct, and other ones, the other one does not. It injects directly into the bloodstream. The effects are the same. It's just the method of delivery, if you will. But what hormones do, almost without exception, they're a messenger. Now, how many hormones are there in the body? I honestly do not know. There are hundreds, if not thousands. Each gland that is producing hormones produces many, and the hormones get produced by conditions. It's like a great example is the pancreas. And the pancreas is a multitask, and like the liver is, though the liver does more. The liver is truly, the liver is unreal. We'll get into that later. The pancreas, of course, and I think most people know this, produces insulin. Anyone who's diabetic knows all about insulin. But what does insulin do? Exactly. Well, in this case, the hormone, which is a messenger, it's produced by the pancreas. The pancreas constantly, the human body wants to keep everything in a normal state, or a state of what they call homeostasis, where everything isn't radical changes. One of the most critical, there's more than one. one that has nothing to do with this, with insulin, is your what they call the pH of your blood. Should be a certain range, and it's critical. It goes higher or lower than that, and you are in trouble. There are mechanisms, which we will get into later, which keep it in that range. Another one that is the sugar level. Or in this case, can you see it down there? Yeah. The glucose. The pancreas constantly monitors the glucose level in the blood. When you eat and you're right from your mouth right into your small intestines where most of your stuff gets absorbed, the digestive system breaks everything down into sugars. And because that is the fuel of the human body, especially glucose, is what's, about 40% of your glucose in your blood is consumed by your brain to operate, for you to think, see, hear, the whole shot. But anyway, the pancreas constantly monitors the sugar level. If I do this standing up, I can't. When the sugar goes up, because you have eaten, well, that's why. But you can easily, as most diabetics know, if your sugar goes too high or too low, it can be bad news. It can kill you. So what happens is when the pancreas sees that the sugar level, the glucose level in your blood is higher than it should be, it creates and secretes insulin, which goes to every single cell in your body. What insulin does, it's a signal, it's a hormone that says to every cell in your body, take in the sugar from the blood, store it. Does every organ, every cell do it? Nope, not at all. Because, I gotta get rid of something. The cells of each organ are different. When the pancreas tells the cells of the body to store excess sugar, one of them is the liver. And it will take that sugar out of the bloodstream and turn it into glucagon. Which is the storage form of sugar in the liver. This is also done in muscles to some degree, not much, but some. It's done by other organs of the body, but the liver is the main one. And this will continue until, and the pancreas will continue to produce insulin until the glucose level has reached, has lowered, because the liver and the other body organs have taken enough sugar, and then it will quit producing the insulin, and that process stops. When the pancreas sees that the sugar has gone low, it will send up another hormone to the liver, which tells it to take that glucagon and convert it back into sucrose and release it into the bloodstreams, because the body wants to maintain that range of glucose for proper operation of the human body. Now, I said that, like insulin, goes to every cell of the human body, including your brain, including your eyeballs, including your kneecaps. Do they all store? No. Each cell, and we're going to get into this later. Let's just pretend this is a cell. And on the surface, when it comes time, I'll be showing you pictures of this, are receptors. In this case, they are insulin receptors. Insulin is a protein. Now, we're going to get into proteins also in the near future. Proteins, when they are assembled by whatever organ and whatever the protein is, assume a given shape. It's hard to believe that when we're talking down in the nanometer range, that shape would make a difference, but it makes all the difference in the world. Insulin has an exact, when it's assembled by a cell and sent out, has an exact shape. And the receptors on the organs that work with insulin have these receptors on them, and only they do. So the insulin attaches here, and then that sends a signal inside that cell to, says, hey, there's insulin. We need to get busy. We need to take in sugar. If this is a brain cell or a bone cell, which stores no sugar, it doesn't have the insulin receptors. So what happens is the insulin tries to attach to these bone cells, but there's no receptor for it. The shape, it doesn't have, there's no match, because the shape of the insulin and the shape of the receptor, it fits literally like a lock and key almost. And if that receptor is not on those, on the surface, cell membrane of that cell, well, then that cell ignores it, doesn't even know. And that's the way it should be. So this is hormones. Hormones are, for the most part, slow acting. And it's not like other nerve transmissions, which can be virtually instant. It can take years. There's a hormone called the growth hormone, which is put up by, if I remember right, the thyroid gland. And if that one works over like the first 18 years, that's why a person continues to grow until they're like 18, until that growth hormone basically gets turned off. So there are hundreds, if not thousands, of different hormones, and with the effects that they have. So, with knowing this and just keeping that in mind as a general thing, okay, that's hormones. Well, what about enzymes? What do they do? The little miracle worker of the human body. All chemical reactions, including those in the human body, happen at a certain rate. And some of them are very quick, some of them take forever, literally. But which is fine if you're not talking about the human body. The human body, often stuff needs to happen almost instantly. For example, every single movement you make, you're using thousands and thousands, if not millions, of enzymes are doing their thing in making a muscle move. Okay? Let me think of an example. There is when chemicals combine, like I said, okay, let's use hydrogen, oxygen. Actually, I know that's not right. Actually, the two should go here. Whoa. My chemistry teacher would be pissed at that. Okay, oxygen. Oxygen makes water. One of the simplest equations known to man. This takes energy. It takes energy to do that. And that goes in. Remember, we talked about bonds in the last video. That energy goes into the bonds, and when those bonds get broken, is when energy is released. Not so much in a case of water, but with every other kind of biochemical inside the body. If you bought, let's say you have one kind of protein. Let's say this is protein, just protein 1. And over here you have P2, protein 2. Now these shapes they're not going to be in this shape, as you will see very shortly. But we're making a point here. And you want to combine these. The body does, because it's going to make a whole new protein, which is what the body needs. But this chemical reaction, which will take energy, if it isn't helped, may take 10 seconds. I'm just using this as an example. Okay? Within 10 seconds, these two will combine to make a P3, which is what we want. What enzyme does, oh boy, I'm going to try and do that's not what I want to do. It's not it either. I know what I want to do, but I don't know how to do it. I know. Here's your enzyme. E-N-Z-Y-M-E. Been a long day. Sorry. Here's an enzyme where this is the surface of it. Here comes chemical number 1, which has the shape and this, do you see how it fits in? Here you got this chemical, which has got this shape. With the end, and these two want to combine. And basically the combining is done right here. But the fact is, the enzyme, what the enzyme does is it speeds up that reaction. It depends upon the enzyme and the chemicals involved. Remember I said before it might be 10 seconds? Down here it might be 1 millionth. Let's do it right. 1 microsecond. A little bit different, huh? This is done, this is called ACTIVATION. Activation energy. This activation energy is the energy it takes to make the two combine, which normally might take 10 seconds, but with the help of the enzyme, what it does is it lowers that activation energy to almost nothing. And they can combine almost instantly. I'll put it this way to you, to illustrate the point. This is one of the most important things as far as your, well, I mean, no two enzymes. You have millions of, hell, you probably have trillions of enzymes in you, which are hundreds of thousands of different enzymes. They all work different. And this enzyme will only combine these two chemicals, whatever they are. any other two chemicals that need to be combined, there needs to be a different enzyme for it. That's why you have so many enzymes within you, and almost all these enzymes are in every cell of your body. Your vision. In your vision, you look, you see, believe it or not, there are hundreds of millions of these conversions being done every split second. You don't know it, you don't feel it, but you see because of it. And if it didn't happen, you'd be blind. This is happening inside your eyes, in your retina, hundreds of, probably billions of times within seconds. And it's what enables you to see. Another example, especially with enzymes. I'm going to try and do this. Once again, I'm no artist, and I apologize for that. And they want, it looks like a button heads here or a hand, but this is a nerve. So that's this space in between them. It's called the synapse. Between every nerve connection in your body, every connection between cells in your brain, there are these synapses. So you have hundreds of trillions of them. When the signal, we'll get into that later. When a nerve signal comes down, you're moving your arm. The nerve signal, of all the nerves are involved. The nerve signal gets here, but it can't get over there because there is this space in between. It is, it's literally like a billionth of an inch, but it's enough. In this synapse, are neurotransmitters. T-R-A-N, not transmitter, no. Sorry about that. Neurotransmitters. That's supposed to be a noun. They carry the signal from the surface of this nerve to the surface of that nerve. In this space in between, on the surface here, is all those neurotransmitters, which are proteins which have already been assembled by the nerve itself. And when that signal comes in, these get released. And they travel literally to receptors on this side. And that carries the signal on. One of the, especially in the brain, one of these proteins is called serotonin, which I think we've all heard of. These, in the case of the brain, these serotonin molecules get to the other side, they produce the effect, and that signal goes down, but this signal needs to end. And they will stay attached here, but there's an enzyme which will break down that serotonin within split seconds after it gets there. After the serotonin's job is done, it will break down the serotonin, which has collected on the side, and then the individual parts of the serotonin go back to this side, and there's another enzyme which reassembles them. So, I just made the neurotransmitters in the nerves of my hand do this God knows how many times. And I hope you get an appreciation for the complexity of what we're talking about here. My whole point in doing this is, we live our lives, and we don't think of our body, or we don't think of it as being the complex. It's so easy to do what we do. But the fact is, you are a fucking, excuse my French, I should have said, I don't care. You are a fucking miracle. What happens inside you to do everything that you do is incredible. The complexity of it. Believe me, trust me, we are just touching the surface of these subjects. It goes very big. As any neurosurgeon will tell you. I don't pretend to know what neurosurgeons do or what they know. I'm sure, they know infinitely more than I do. But it's to give you an appreciation of how complex it is and how fragile you are and how things can go wrong. So it's an incredible miracle that we live as long as we do and everything works as well as it does. Now, as an ending note for today, remember I said about the proteins? The proteins literally, there's, I don't know how many, hundreds of millions of them that are in our bodies, different kinds. They each have a different job. And each one has a different shape because there's different receptors for them. As their hormones, there's different receptors for them. But it's the electrostatic charges in individual atoms that make up the protein that it will take a particular shape. And to illustrate that, this is just a cover from a book. It says medical biochemistry. Look at that. That's a protein. Which one? That could easily be insulin. For all I know. Matter of fact, insulin, I'm not saying it is insulin, but insulin looks very similar to that. It's crazy. Okay? I just want you to get an appreciation for the complexity that is you. And we'll try to continue to break down that complexity on the next video.